Oh, thank you very much, and thanks to all the speakers of this session for these very interesting presentations. We have now a few questions. You can also directly ask questions to the authors if you have a very specific question via the chat. There is a way that you can directly address the paper or go to the paper and then directly go into the Q&A and then ask a question there. A few questions have already been asked, and I want to now moderate a little bit these questions that are still left, basically, and some of them I take the freedom also to bring them probably to a more general level. So basically starting probably with the question that I have on the screen right now, which is about the limitations and barriers here. The usage limitations for the Game Boy, but of course for anything that is energy harvested, yeah, you rely on the harvested energy, yeah, which is clear. And so the question is here, in the specific case for the Game Boy, what is the speed? For the interaction papers, it is more what type of interactions, and part of it has been addressed in the talk, what type of interactions are possible, where are basically the borders that are unlikely to be crossed in the next few years. Yeah, that would be interesting questions. So probably we start with Jasper de Winkel, which can directly answer these specific questions for the Game Boy, and then continue with the other participants that presented energy harvested systems, what they think is basically yeah, the limits of this technology.
Well, thank you. Can you hear me? I hope so.
Yes, yes.
Very good. So the Game Boy operates very close to real time, actually. So it's very hard to discern the difference between a real Game Boy and the battery-free Game Boy. So in that sense, of course, as you said, we still are limited by energy harvesting, right? So if there's not enough energy, then you will start noticing the off time more and more. And of course, you cannot do anything when the system is off. So maybe Josiah, you can add upon this, because I know you want to.
Always. I mean, yeah, if with the Game Boy, which, you know, there's a plug right there. We have it in blue as well, and orange. I mean, it does depend on, you know, the type of game, the type of environment at kind of just the Game Boy specific level. When I'm comparing me playing Tetris on my original, you know, Nintendo Game Boy from like way back in the day, it's pretty close. I mean, we've measured that it's a little bit slower in terms of executing, but that's, you know, partly because we're emulating an entire hardware platform, right? Whereas the Game Boy was just directly executing the binary code, right? I think in terms of like the future, the Game Boy is just, you know, it's one step, right? And we can take intermittent computing devices, and we've seen two other great talks that, you know, harvest energy and do machine learning tasks that help to make decisions for kind of these more classic wireless sensor network problems of deploying something on farms and smart cities and things like that. But I think with this, we're also saying that, you know, batteryless energy harvesting devices, maybe those that are harvesting energy from body generated sources or novel materials, are also useful for this whole interactive Internet of Things. And this brings us to a bunch of interesting questions about, well, a Game Boy is cool and cute, but what if we have interactive devices that are, you know, the labels on my food, right? Or the wrappers that I'm putting things in that are giving me sensing values from, you know, the Burger King I got. Oh, I probably shouldn't say Burger King, from fast food or something like that. So I think we open up kind of the potential, you know, limits and thoughts of what an Internet of a trillion battery-free things, more sustainable batteryless devices could do that could aid society without causing this gigantic, you know, e-waste and ecological debt from from having all these batteries in the environment. Because while there is a very large supply of lithium, we have a very finite supply of water to help extract that lithium, and that directly affects indigenous people like myself and others who, when you can't drink water and you can't eat food, what are you going to do? You don't need a smart device. So I think that's kind of some of the vision that at least I see, but I'm definitely interested in what others think of these kind of sustainable devices and where they're going.
So who wants to jump in?
Ding Chen, Anand, take a shot.
So yeah, let me talk a little bit about Optosense. So basically, we are trying to use the opportunity presented by the material scientists that they make this kind of organic semiconductors that can harvest energy much more efficient than the silicon semiconductors in indoor locations, right? So they have much higher theoretical limitation of energy harvesting efficiency of, I think currently it's like 26% efficiency compared to the ones we are using in the video, which is like commodity solar cell, which is like 3.4% for indoor lighting conditions. So they can harvest more energy. That's why we are trying to collaborate with them. And also, so if you can harvest the same amount of energy with like 7-8 times smaller, and that basically means you can do more things with them. So yeah.
I want to add to that. The advantage of battery-free systems definitely is good for the environment. No batteries, no lithium, and to make it efficient and like better performance. Of course, there's research going on having good materials which are more efficient at harvesting energy and things like that. But I think my overall view over a battery-free system is that you're reducing the energy, so you have to trade something for that. It could be performance, it could be some kind of user experience or something. And that trade-off is something you as a designer, researcher, engineer can decide what you want to trade off in that system. And one advantage we have here is like our systems are not black box systems, but something which is being interacted by users and a kind of HCI system. So we have a kind of flexibility there on how do we want to design the application, how do we want the system to interact with the user, so that this trade-off is not like a limitation to the system, but we design our system around that. One quick example was like in my paper, which was UbiComp, and we designed battery-free touch interfaces. It's extremely low power. And what we traded off was the speed. It has a high latency than the traditional touch interfaces we use, and an error rate. It also has a high error rate. And we looked at these problems to design by making the interactions longer and things like that, adding redundant features. So I think that's also an important aspect for battery-free systems, to think in the application domain and like augmenting to solve this, to help reduce the problem because of low power.
So I want to add on top of that, it is true that there are some aspects we have to compromise to make the intermittent systems usable for us. But that's another interesting area to work on to see how we can do that. Because it's not only the environment where the current technology is moving us to a sustainable system, but if we think the advancement in like a medical system, that continuous monitoring is helpful, and there are some products in the market which has built-in glucose monitoring in your hand, and you put your phone close to it to read the glucose amount in your blood sugar whenever you want. But that's not actually all you need, because studies show that if you continuously monitor, there are some people whose blood sugar suddenly drops, and it indicates to some specific diseases. So there are some, and you cannot ask a person, okay, put a battery in your body and change it every month, or have 10 devices on your body and then change it. So this is something where the aspect of batteryless or more sustainable system comes, that it makes the users avoiding the burden of changing the batteries. And the works that I think a large amount of work is also needed to see how can we minimize the trade-off. For example, like in my work, Zygote, what we did is we were trying to minimize the trade-off between the energy and the performance and time. So the way we're doing that, we are trying to identify how much work do we actually need, because because many of the works are redundant and it varies how much performance that the system needs. So these are, I think, a very interesting area or the aspect to see that how we can minimize this trade-off and make the system more closer to a persistently powered system.
Okay, thanks a lot. Anything to add from the others? Otherwise, I will proceed probably to another question. It was more about the hardware and what we think would be the way to go. Yeah, here was about custom ASIC. There was novel material also mentioned. I want to add one thing, which I think is important, because it is so obvious that there is need for more self-powered energy harvested devices. How open are your basically your designs? Do you open them like open hardware so that others can learn from it? Yeah, probably most of you have had a hardware piece on it. Please give a short comment on where do you see the future for the hardware will go, yeah, in terms of technology, and whether you are able to open your system, or probably it is already opened so that others can learn from it.
I can add to this. So my shot at this is that in order to make low power systems, it's very, very important that you optimize on the hardware some way or the other. Either you optimize the power harvesting or whatever is doing the computation or sensing part of it. So we can look at novel materials which can like self-generate power and augment the system's requirements. Or in terms of hardware design, we can, for future hardware design, I think we can look at systems which are built from discrete components without dedicated, not general purpose system, like using microcontrollers and things like that, because they consume power, but design systems for a particular special task with very low component count, and that would immensely help to save power. And that could be one of the ways to like build inexpensive disposable devices which run on a very low power budget. And for my project, we intend to open source the software and hardware design for this project, so people can try it out and try to build something, play with it.
Very good.
I think there's you gave a broad question, then very specific questions, right? Obviously we have a GitHub repo and you can create your own Game Boy. If we tried to sell them, I think we would get a cease and desist letter from Nintendo. Although I think the best comment we got, this is probably from Twitter sphere, was that, oh, this sounds like something crazy enough Nintendo would do. So I did appreciate that. But designs are all there for anyone to build it, and it is manufacturable with some skill. But I guess the bigger question is, what is the future of these components? Like, a lot of the previous work has used, common off-the-shelf type components, things you could readily buy. That has like kind of the benefit of, okay, now anyone can go build these systems that we're designing, and that's great for saying, well, here, you try and make some battery-free devices and deploy them. But obviously, combining ASICs with non-volatile memory that's coming out, so an ARM chip on an ASIC with non-volatile memory that's mapped right into the address space, that's 100 times more power efficient. That's really where much of this will have to end up if we want to see it at this trillion scale that the NVIDIA CDO said yesterday or 2 days ago on the merger that where the Internet of Things is headed. So I think kind of that push will have to happen, and we'll see a lot of those new ASICs come and trickle back to kind of those of us who play around in COTS land. And I think we just have to engage with collaboration and try and make sure that we're working with people that are building these novel energy harvesters and with people that are building these new ASICs to explore new applications beyond, you know, the fun stuff we're already doing now, right?
Others want to join in that have built hardware?
Yeah, I think for Optosense, we benefited a lot from the improvement of like the ARM processor that, you know, features this kind of low power capability, especially that they can, you know, directly acquire the signal from the ADC and then just store that into the memory. And then, so we try to make the CPU sleep as much as possible, and then sending the information only when it's needed. So I think definitely the trajectory of the industry is constantly improving the commodity hardware on low power perspectives, and I think they also helps us to build prototypes much quicker.
Okay. Somebody else? You also had hardware. You want to say something? Is your hardware design also available?
Okay, I'd like to add on that. And in terms of if it is available or not, actually, it's not available yet, but on the internet. But we of course want to make this technology used worldwide. So we're planning to make this open. And another aspect, another question about the ideal hardware thing. The one we really struggled with was that there's actually a very a huge gap between the ASICs and the non-ASIC discrete ones, and we would like to make our hardware very power efficient but also very high performance, but ASICs are only made for the mass production things, for all for example for the smartphones, but other things that are for example for our purpose, our the thing we wanted to do was very niche if it was seen from the mass markets. So I think if there was kind of a much more easier process to if it's there was a process to make the ASICs more reachable. I heard that Google is trying to make the ASIC process open source. So I think if those kind of movements get larger, it more researchers can get involved into making ASICs, and these low power applications will get extend further. Thank you.
Thank you. Somebody else wants to say something on that issue? So another, say, question block was around basically the usage of the technology and how much of, say, the situations probably the technology may be used needs to be covered. Yeah. Also in terms of what experiments do you have to do to sort of prove that the ideas that you have is really working in situations like if you have something that is doing with activity recognition. Of course, you have to be real-time capable. How much do you have to prove that for all the situation? But it can also be extended to, for example, the bus lifetime system, where you never know exactly, of course, yeah, how in the future, yeah, the behavior of people are, and thus basically the algorithm is really appropriate for these new novel situations which are not trained. Yeah. So what is the basically the limits that we can do in terms of experimentation in our research paper, and how far should we go? Yeah, and I probably want to give this back to you to hear your opinion. Yeah, how thoroughly do we need to test every thinkable situation, or is it okay if we say specifically these situations we selected, and in these situations our system is working to a certain extent? So this is a question basically to everybody.
So I can start with my comments that I love that it can be twofold. So at first, we do need to have more extensive evaluation on how the system works and prediction and estimation. But in addition, we will also need the system to evolve with the environment, because as you mentioned that the future is unpredictable. Like however we predict, there can be some components in the future which we never predicted. For example, that this 2020, we have COVID. In 2019, many of us did not predict how our life will go in 2020. And in such systems, which we are thinking of to be sustainable system and deploy in, let's say, a large scale, or in scenarios where it's hard to change or update, the system need to have some self-adaptation and need to adapt with whatever is going on. So there is a huge need of learning. So in the future, it can be a part of the lifelong learning. That's a vision that the research community is moving forward.
Okay, thank you. Who wants to be next to tell us his opinion?
Mikhail, I'm not sure I'm going to directly address your question, I think, but what an interesting observation about the paper we had in this session is they addressed issues of power. They addressed some, particularly that last paper, an issue of form factor. You know, if we're going to have these things embedded throughout our environments, we're going to have to be concerned with what they look like and how they get embedded. What we haven't addressed as a community is how we're going to get to the trillions that the Game Boy folks were talking about, this internet of trillions. And that gets at the manufacturing procedures that have to be used and the materials that we're using to produce these items. And I'd like to hear other people comment on that.
Very good point. Probably from those that haven't stepped forward so far.
So I can chime in a little bit. So in terms of the scalability, so Optosens definitely has looked at that. And basically we are saying that by moving from the traditional silicon, subtractive processing to more of additive manufacturing, and that basically can reduce a lot of the cost of manufacturing large scale devices like solar cells or photodiodes. So basically, the advantage of the material we're interested in, like organic or perovskite, as they can be roll-to-roll coating. They can be compatible with a roll-to-roll coating, and they can be processed using liquid solutions, and they can be processed under room temperature. So that saves a lot of the energy and in the manufacturing processes. So I think so we need to look at especially how the devices like individual components manufactured and how they can be scaled to trillions, or like in our words, it's like surfaces of everyday objects. Yeah.
So I was thinking of this from, I guess, we can go along with reaching trillions by relying on manufacturing techniques to be put into, giant large scale processes, right? So you have these, many $100 billion fabs, right, that would make these work, and then you could get that scale. But this community, I feel, is very good at, the DIY technique, right? Do it yourself. And so I wonder how we can advance, and I hope we can advance, how new energy harvesting modalities and materials could be assembled from, a bucket of soil, maybe, or from a few things you can get at a hardware supply store, or water, like 3D print a little micro turbine, right? And so I think that possibly that's one intermediate way to scale, because if you can scale by centralizing everything in one place to build it all, or you can scale by having 5 billion people be able to make their own computational devices that they could then use to benefit their own daily life. And I think that's very interesting and inspiring. And if you build these types of systems that we're talking about that harvest energy, they become much closer to this kind of perpetual, smart dust vision that was, come up with by the person who named this conference, right? And I think that's very interesting. I think the relying on people and democratizing the development of these devices themselves is very, very interesting and exciting as a potential direction, I think, for everyone in this panel. I guess on the testing side too, to make that happen, we have to have some way to take a lot of the things we've talked about, because we've talked about a huge kind of array of devices and systems in just this panel. I mean, it's glorious, right? How can we come up with things like, what's the Mi Bench for sustainable devices? So Mi Bench was this great embedded systems computing benchmarking suite, right? What are the new Mi Bench tools that are energy aware? Because now we have this whole dynamics of energy. How can we quantify and classify energy harvesting devices generally? How can we replay, record energy harvesting? How can we design, for us, we were thinking, is Game Boy now a new platform that you can test out different things? Even if you don't run an emulator, you have this piece of hardware that we can all compare against. Like, what is that future for benchmarking that can enable this democratization of battery-free IoT?
I agree with everything you said there, except the point about relying on these mass scale fab locations. That may be possible, but I think actually we're going to have to, and I've been influenced by my colleagues here at Georgia Tech in chemical engineering, who are saying, think about bulk-oriented modular manufacturing practices that are done in almost all industries other than the integrated circuit industry of computing. And when we get down to the level of these materials, we can actually start thinking about different ways of assembling they may not produce the super computers that we're thinking about, but for these much lower demand computational activities, that's probably the way to go to get to the trillions, quadrillions, and beyond.
Yeah, and probably the computing can be distributed. So if you distributed it, energy harvested devices, it would be also a great thing. So probably one person haven't said so much. Song Yang from the electric bus battery. Is it possible to have heavy, algorithms like you developed to distribute them among a lot of small devices, say, that are then energy harvested? Oh, he's muted. So probably audio problems. So somebody else from those that developed algorithms, ML algorithms, want to jump in?
So I believe that it is possible, and it has a huge, it can be a huge thing if we can decentralize the computation from one device to multiple devices. It also comes with more challenges because if you think about how the cloud computing work, there's several servers, and the way they work, they have some communication going around there. And that is one of the most costly thing that goes around with intermittent system, because radio modules or communication is usually costly. So this is a very interesting area to see that how we can trade off with the amount of communication we need to do and allow the systems to work in a distributed way. So probably in the future we might be able to do something, distributed nodes, or multiple distributed nodes doing a single work with minimal or no communication at all. So that might be an interesting thing to look at.
Okay, yeah, thanks a lot. I think we have now reached the time limit for our session. I want to again thank all the speakers, especially also for answering the question and answers. Yeah, thanks a lot. And I think this was a really inspiring session, at least for me, I guess, also because we have a lot of viewers also for the audience of the UbiComp, obviously. And we can continue talking about that topic in a booth in Gather.town. So you can meet us on the social terrace and on booth A. Yeah, and then we can continue asking general questions, but also specific questions to some of the authors of the specific papers. I will try to go now to Gather.town myself, but probably I'm not the first one who will reach the booth. Yesterday, it took me like 15 minutes until my little man has started working. Yeah, I don't know why, but probably others can just straight go to the booth A in the social terrace.
You go to private gatherings on the terrace, booth A.
Okay. Yeah, thanks also to the SVs, yeah, to jump in and solve the problems that have suddenly appeared. Yeah.